Okay, so first thing I want to do in this problem, I want to change t equals 3 to t equals 1 just because the picture will show up a little bit better for what we want to do. Um, Now in this question, we're asking for an instant rate of change of a function at a specific point, whereas in the previous problems, we were asking for the average rate of change, which is just you figure out where you want to take the average rate of change from what to what. You draw that line through those 2 points on the function, and then you figure out the slope of that secant line. Well, I could say find the average rate of change from 1 to 3, or find the average rate of change from 1 to 2, or find the average rate of change from 1 to 1.3. The idea that I'm getting at now is how do I get the instant rate of change right at 1? How fast is it changing just at the point where x equals 1? So, or t equals 1 in this case. So the way that we do that is we actually take t equals 1 right here. So this point is 1 f of 1. And we pick some other point over here, let's say. So like a f of a. And then if I wanted to find the average rate of change, then I just take the line through those 2 points. So let me draw that in. Whoop. So there's the line through those 2 points. But if a gets really close to 1, so if I actually move this point closer and closer to 1, right? At some point, that tangent line, that secant line that I'm drawing starts to look more and more like a tangent line. And to prove it, I've got this sketchpad thing here. So here's A. That's the point. That's like the point 1 f of 1 on the previous picture. This is a different kind of function, though. So I'll make this a little darker. Display line. What I'm doing is I've got, here's my run and my rise. And over here you can see all the numbers that go with it, but that doesn't really matter for this diagram. I'm going to pull that line in. Right now, if I figure out the slope of this line, that is the average rate of change from A to B on this graph. And so if I continue to move this closer and closer and closer, look at what happens to that secant line. And then when I get so close that it's practically on there, it turns into a tangent line at that point. Right? Okay, so let's go back and figure out how to do that on this diagram. Whoop, sorry. There we go. So again, the idea is you pick a point that's kind of far away, not too far away though, something reasonably close, right? And we're going to figure out what the slope of that secant line is. So the method is find the slope of the secant line through 1 f of 1 and some other point, a f of a, right? Then make a get close, so the point a, right? Get close to 1. And that makes the secant line, so the secant line will turn into a tangent line. And instead of getting an average rate of change from 1 to A, you end up getting an instant rate of change with the tangent line here at 1. Okay? So that means, we'll write this too, that means that the average rate of change will turn into, from 1 to A, will turn into the instant rate of change at 1. Right? These are like t values here. Okay. So the slope of the secant line through those 2 points is f of a minus f of 1 over a minus 1. So that's the slope of the secant line, right? So in order to get the slope of the slope of the tangent line, then we're going to do this. Slope of tangent line at x or t equals a. That is going to be the same exact thing, f of a minus f of 1 all over a minus 1, except that I'm going to make a get closer and closer to 1 to force that secant line to turn into a tangent line. So let's figure out what that is. That's going to be limit as a goes to 1 of, now f of x is x squared, so this is a squared minus 1 squared over a minus 1. Now I can't just plug in 1 into that thing because it's undefined at 1. But if we factored the top into a plus 1, a minus 1, then you can actually see that the a minus 1s would cancel, so it's just a removable discontinuity there. And if I cancel them, I fill in that hole, and now to figure out where that hole would have been, I just plug in 1 into what's left over, and I get 1 plus 1 equals 2. So what that actually means is the slope right here at this point, right there, the slope of that tangent line is 2. Okay. Now if this equation represented our position at some time, so if f of t equals your position at time t, then what we did was we just figured out a slope, right? So the slope of the tangent, at t equals a is really given by this limit here. It's this thing, right? It told us the rate of change, the instant rate of change of position in terms of time, right? It's, in fact, you can think of it this way. Excuse me. Remember the slope, the units of the slope, if this was like seconds and this was meters, then I'd be looking at a change in meters over a change in seconds. And that gives me an average velocity, but I actually turned the seconds into an instant. The change in seconds became a single instant. So it actually gives me an instantaneous velocity. Up above, when we did the average, right, the average here, this represents the average velocity from A to B if the function itself is position. Down here, if the function is position, then the tangent line slope is the instant velocity. It's how fast I'm moving when t equals 1. Okay, now I want to look at a second method for doing the same problem as above, right? But instead of calling it a f of a right here, I'm going to call it something else. So we're still looking for the slope at 1, right? Excuse me. Excuse me. 1 f of 1. And I'm going to pick some other point over here and figure out its secant line equation for the slope, right? But instead of calling it a f of a, I'm going to call it 1 plus a little bit, because it's over to the right of 1. And I'm going to say f of 1 plus a little bit. And so the slope of the line that I'm looking at is this one, this secant line right here, right? Not the straightest line, but you get the idea. And I'm trying to figure out how to turn that into this tangent line instead. And the way to do it is to make this point approach that point, right? Just like we did in the previous problem. So that's the same thing as saying make h turn into 0, because right now it's like 1 plus a couple units. But if h turns into 0, that 1 plus a couple units turns into 1 plus 1 unit, 1 plus half a unit, 1 plus a tiny amount, and pretty soon it's lying right next to this point. And this secant line will turn into a tangent line right there instead. And that's what we want, the slope of that tangent line. So right now, let's write out our equation. Let's see, the slope of the secant line from t equals 1 to t equals 1 plus h is given by f of 1 plus h minus f of 1 over 1 plus h minus 1, which is f of 1 plus h minus f of 1 all over h. Okay? So what I want to do is find the slope of the tangent right here, because I want the instantaneous rate of change. So instantaneous rate of change at t equals 1 equals the slope of the tangent at t equals 1. And that's really the same thing as the slope of the secant line that we just figured out, f of 1 plus h minus f of 1 all over h, except that I want h to get smaller and smaller and smaller so that eventually this point turns into that point, or approaches this point, and my secant line approaches a tangent line instead. So as h goes to 0. Okay, so let's figure this out. So this function right here, or this limit right here, limit as h goes to 0. Remember, f of t is t squared, so f of 1 plus h is 1 plus h squared minus 1 squared all over h. And then if I FOIL out the top, I get 1 plus 2h plus h squared minus 1 all over h. And then these 1's will cancel. And if I factor out an h, I'll get limit as h goes to 0 of h parentheses 2 plus h all over h. And this function right here has a hole at h equals 0, but the rest of it looks just like 2 plus h, so that when I get really close to 0, I can just use the 2 plus h to figure out where it's actually, where that value is, and it's 2 plus 0, which is 2. And so that means that the instantaneous rate of change at t equals 1, or the slope of the tangent at t equals 1, is 2. So right here, this line has a slope of 2. So in general, let's talk about what this means. So in general, if I've got some function here, and I want the instantaneous rate of change right here at a f of a, this is what I want, right? So instantaneous rate of change at x equals a, where this graph is f of x. Okay? So the way to get that is to find the slope of the tangent line at x equals a. Okay? And the way to get that is to do one of two things. One way is the slope of the secant line through a f of a and some other point here, which we'll call b f of b, and you want to let this point turn into that point so that the secant line turns into a tangent line there instead, and let b turn into a. So that's one way of doing it. So I'm going to say this is 1 right here. The other way of doing it would be take the slope of the secant line through a f of a And instead of calling this b f of b, you could call it a plus a little bit f of a plus a little bit. And so you're taking that point as your second point, and a plus h, f of a plus h. And you let h turn into 0, because then a plus h will eventually turn into a. So this would be the second method. This would be another way of doing the same sort of thing, but with slightly different calculations. So these guys right here, if we actually come up with those formulas, the first formula, these all equal limit as b goes to a, because we're making b turn into a, and then it's the slope of that secant line, f of b minus f of a over b minus a. And then the second version would be limit as h goes to 0 instead of f of a plus h minus f of a all over h, right? Or, sorry, let's do it this way. A plus h minus a. So it's y2 minus y1 over x2 minus x1. And then that can always be simplified because of the denominator there into just h. This tends to get used more often. This one, not quite so much. I know this bottom one looks a little bit worse, but it turns out that it's way easier to cancel out that h than it is to try and factor out a b minus a every time. So, okay, hope that helps some. Okay, so I thought of one more thing that I wanted to add. If f of x equals your position at time x, then what we figured out also was that the instantaneous rate of change of f, well, that's really going to be a change in position over an instant change in time. So change in position over change in time is a velocity, and this gives you your instantaneous velocity at time x. Okay, so this is the one last piece here that we need. Okay, that's it.